Welcome back, Calculus and Vectors class. We're going to go into 6.5, which is where we're going to take those simple differentiation rules that we learned in the last lesson and see how they apply when we throw in other rules. Because we know that in calculus, we can use multiple rules all at once. So let's start with the first function, which is y equals x times e to the x. So right off the bat, you should see that this is two smaller functions multiplied together. So it seems like product rule is going to be the best plan of attack here. So product rule here. So what we're going to do is we're going to take the derivative of each of the functions and multiply it by the other function. So we're going to do 1 times e to the x plus x times e to the x. And that's going to be, we can common factor that. We can common factor out e to the x, 1 plus x, or x plus 1, however you want to do that. So that's how you would deal with that type of problem. So it's really just a matter of looking at each type of problem, figuring out what type of rules you're going to use to help you. So the next one we have y equals e to the power of 2x plus 1. With this one, we can replace that. That almost looks like e to the x, but it has a little bit inside in place of the x. Because it turns out this is a chain rule problem with the exponent being the inside function and e to the x being the outside function. So that's e to the u, where u is equal to 2x plus 1. So this is going to be, to find the derivative, we're going to take the derivative of the outside function. So that's e to the u, and then multiply by the derivative of the inside function. So 2, that's going to be 2e to the u, or 2 times e to the power of 2x plus 1. Next one, we have y equals e to the x minus e to the negative x. So a few things happening here. We have two functions that are subtracted, so we can just take those derivatives separately. Let's start with that. The first term is nice and simple. We said that the derivative of e to the x is just e to the x. Then we're going to subtract. We're going to find the derivative of the second function. So that's going to be, we have a negative x inside, so we can't quite do the same thing. So for this part, we're going to have to use chain rule again. So in this case, e to the u is the outside function, and the inside function is negative x. So that is going to be, the outside function is going to be e to the u, and then we're going to multiply by the derivative of the inside function, which is negative 1. That's going to be e to the x plus e to the u, or in this case, e to the negative x. So hopefully these are starting to make a little more sense, but just a matter of looking at each one and analyzing it as you go. So for the next problem, we have y equals 2 times e to the x times cos of x. So now we have some trig thrown in there. But as it turns out, it works out the exact same way. The same rules apply, and we can use exponential rules and trig rules in the same problem. Before we do that, though, we have to look at the overall problem, and we should notice that there are two functions multiplied together. So we're going to use product rule. So take the derivative of each function and multiply with the other. So the derivative of the first function is 2 times e to the x times cos of x. And then we're going to take the original first function, 2 times e to the x, and multiply it by the derivative of the second function, times negative sine of x. So that's going to be, let's start by factoring out that 2 times e to the x, because that's nice and simple. And then we have cos of x minus sine of x. So not too bad. So let's do one more. Now we have y equals x squared times 10 to the x. Again, we have 2 multiplied together, so product rule is going to be the way to go. So y is going to be equal to, take the derivative of the first function, 2x, times the original second function, then add the original first function, times the derivative of the second function. The second function, that's going to be natural log of 10 times 10 to the x. So now that we've done that, let's see what we can factor out here. We could factor out, we have an x in each one, and we have a 10 to the x. And then once we get rid of those, we have 2 left over in the first term, and we have an x times a log 10. But let's rewrite that as natural log of 10 of x, just because we like to have coefficient on the front. And that's all there is to it. So when you're doing differentiation problems, the biggest piece of advice I can give you is just look at it as you would any other type of function. See if you can apply product rule, chain rule, or quotient rule, and then use those extra rules for trig functions and exponential functions to help you however you need them to. So now that we've done a bit of practice with that, make sure you do some on your own. But let's try some more specific examples, some better application problems. So example 2 says identify the local minima and maxima for the function y equals x squared times e to the x. Now think back, local minima and maxima, that's going back to curve sketching. That was something that we saw there. And we said to do that, we just set the derivative equal to 0. So let's take the derivative of that function. So y prime is going to be equal to x squared times e to the x. We're going to use product rule because we have 2 pieces to this. That's going to be 2x times e to the x plus x squared times e to the x. And when we factor that, that's going to be x times e to the x times 2 plus x. We just factored in x and we factored in e to the x, and that's what we get left over. So now that we have that, now let's set that equal to 0 and see what happens. X times e to the x times 2 plus x. So this looks a little bit weird, but you notice how we have these different things multiplied together. And we know that the zero product rule says that when we have different things multiplied together, just like with the parabola when we factor, we can set each individual one equal to 0. X equals 0, e to the x equals 0, and 2 plus x equals 0. So x equals 0 is already done for us. E to the x equals 0, so think back, is there any values that we get there? We could try taking the natural log of both sides. But we know that we can't take the natural log of 0, so it turns out this one does not exist. So it doesn't actually return a value there. And then we have 2 plus x equals 0. So x equals -2. So we could have a potential minimum or maximum at 0 and 1 at 2. So just like before, we're going to make a factor table to help us out here. So let's take, we said that we're going to have a region to the left of -2, and then -2 to 0, and then x is greater than 0, everything to the right of 0. And let's take a look at what happens with each of the factors in our derivative. So for y prime, we had an x, we have an e to the x, and we have a 2 plus x. So think back, with curve sketching in each region, we just picked a test value. Say x equals -3, and then x equals -1, and then x equals 1. And we're going to test them in each one. So just to help speed this up, it's going to be negative, positive, negative, which means that this is going to be positive or increasing. And then we're going to have negative, positive, positive, which means that we're going to be negative or decreasing. And then we're going to have a, let's see, positive, 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 which means that we're going to be positive or increasing. So that means that we're going to have a local minimum at x equals 0 and a maximum at x equals -2. And to find the y values, we just plug them in. So y equals 0 squared times e to the 0, which equals 0. And then for -2, we get -2 squared times e to the -2. And then that's going to work out to somewhere around 0.54. So we have the coordinates for our minimum and our maximum, and we can plot those on a graph, which we see down here. We have, let's see, we have -2, -2, and 0.54. And then we have 0, 0. As it turns out, even though we just used the one portion of curve sketching, all those same different principles that we used for curve sketching, all those tools that we learned about, you could actually use them in a curve sketch, and you could actually replicate this function or any other exponential function now that you know how to differentiate it. And actually, the same with trigonometric as well. If you know how to find those features, then you can use those to help you reproduce a graph with the curve sketching methods that we learned already. So let's continue on. Example 3 says that Karen has just bought a new motorcycle for $10,000. The value of the motorcycle depreciates over time. The value can be modeled by the function v of t equals 10,000 times e to the -t over 4, where v is the value after t years. At what rate is the value of the motorcycle depreciating in the instant Karen drives it off the lot? So it's saying at what rate is the value of the motorcycle? So when you hear rate, you should think rate of change. So we're asking for the rate of change of the value of the motorcycle. So we're looking at the rate of change for that value function. And we're looking when she drives it off the lot. So that's time 0. So essentially, we're trying to find the derivative at time 0. So that's not too difficult. We can take the derivative. If it was 10,000 times e to the -t over 4, let's see, the 10,000 a constant multiple, so it stays the same. And then for e to the -t over 4, we're just going to use some chain rule. That's going to be e to the -t over 4. And then we do the derivative of the inside function, which is just our exponent, this part here, and that's -1/4. So next, let's clean this up a bit. Let's multiply the 10,000 by the -1/4. That becomes -2,500 times e to the -t over 4. So now that we have that, we can plug in 0 for t. That becomes -2,500 times e to the -0 over 4, or -2,500 times e to the 0, or -2,500. And that's going to be -2,500 per year, which essentially just means that when we start the first year, we're losing $2,500 on average per year. So therefore, the motorcycle is initially depreciating at a rate of $2,500 per year. Question B asks, Karen decides that she will stop insurance coverage for collision once the motorcycle has depreciated to 1/4 of its initial value. When should Karen stop her collision coverage? So we're trying to figure out once it's reached 1/4 of its value. So we're looking for the point, let's see, initial value was 10,000. So the 1/4 of that we're looking for when the value is equal to 2,500. So in this case, it's not really asking us anything about the rate of change. So we don't need to use the derivative. We're just going to plug that in for v of t, the original function, which was 10,000 times e to the negative t over 4. And then we're just going to solve for t, where we want to find the time. It's asking when. So we moved the 10,000 over, so 2,500 over 10,000 equals e to the negative t over 4. So that's going to be 1/4 equals e to the negative t over 4. So right now we're going to use that little trick with logarithms where we're going to set both sides equal to natural log. Or we're going to take the natural log of both sides. And that way we can take that exponent and we can move it out to the front. So natural log of 1/4 is equal to negative t over 4 times the natural log of e. And of course the natural log of e is 1, so that just goes away. And then we're just going to move the 4 and the negative over, and it becomes negative 4 times the natural log of 1/4. And that's going to be equal to t. So when you calculate that out, that's going to be roughly 5.5 years. Therefore, she should sell her bike after 5.5 years. And lastly, at what rate is the motorcycle depreciating at the time determined in Part B? So it's asking the rate, so we're going to use the derivative. And we're going to find that at 5.5 years. So that's going to be, we're going to take the derivative that we found in Part A, which was negative 2,500 times e to the negative 5.5 over 4. Punch that in your calculator, and you get negative $625 per year. So at that point, at 5.5 years, the bike is depreciating at a rate of $625 every year. That's pretty much it. As long as you know your differentiation, you know your log rules and your exponent rules, then trying to deal with these problems is not too much more different. It just looks a little bit different, but essentially the same principles. So make sure you do some practice, get comfortable with it, and then we will do one more lesson in 6.6.